Okay, now Friday we did some basic simulations on 5.4 on current and resistance. And that's what this is going to be a little bit about. Now, if you think about current, so you've got this material and this copper wire, aluminum wire, I don't know, whatever you want it to be, and but it needs, most likely it needs to be metal, and it has, and you're going to create a potential difference across it. So from one end to the other, there's going to be a change in voltage from here to here, and due to that, you're going to get some electron flow. So I'm going to use a different color here, and we'll just use yellow, and so you're going to have electrons in here, and these electrons, let's just say that this is at 20 volts, and this is at 10 volts. So because of this, and as you could see, remember in the simulations they had batteries, and you had to have a battery hooked up, that you will get these electrons will flow in this direction, in this general direction. But an interesting thing is that they don't just go straight. There's actually just an electron drift, because they're going to bump into other electric fields, be, they're just sort of going to go off in a little random direction. But in general, they drift in this way, in this general direction, from high potential to low potential. And so what we call that, when we get this general electron drift from high potential to low potential, and how much many of them will drift and how many of them will go in that general direction is dependent upon the potential difference and the properties of the wire going through it. If it's a really good conductor, the same potential difference can get you a little bit more current out of it. So this is what we're going to call current. The movement of electrons through a conductor, but they're going to drift because of the presence of other electric fields in there that are going to disrupt their general directional, in a straight line. So they're going to get a little bit of opposition, and that's what could help create a little bit of resistance that we can also talk about a little later. So this is current, and I'm going to change back to red. It seems to show up better. And so current is equal to the change in Q over the change in time. So just think about it. It's just a rate. That's all it is. It's how many electrons flow through a wire in a given unit of time. And we call that current. And we're going to measure current in terms of amperes, or the ampere. And the abbreviation for current is going to be I. The symbol, for current, is going to be I. So get used to that. If something has 20A, then that would mean that it has 20 amperes. And that means 20 coulombs are going through the wire or the conductor per second. Wow, that's a lot. Because remember, 1 coulomb of charge is 6.25 times 10 to the 18th electrons. So that's a lot of electrons going through there. But still, it's just a rate. That's all it is. So not much to talk about with current. Make sure you read the book on 5.4, and they talk a little bit more about electron drift and other little aspects of the current flow. Electric resistance, you were exposed to the other day in terms of Ohm's law. And Ohm's law, if you recall, was V is equal to I times R. And so as you can see, we have a proportional relationship between if you keep resistance the same, and here let's just go ahead and show you what you had the other day. So you have a battery. This is a symbol for a source of a voltage potential source. This is the positive side, and so this would be this would be the symbol for like a battery, and here's your resistor. That's a symbol for a resistor. That could be any kind of load on the circuit. And then I'm just going to bring it right back to it to make a circuit, a complete circuit. So if you were to keep this R constant, and R is measured in ohms, R is in ohms, and the symbol for that is the horseshoe. That's sort of a weird looking one. There we go. and we'll correct that a little bit. There. Then we would see that there would be a proportional relationship between V and I. That's assuming that this is ohmic, that this is an ohmic substance. So, and you can see it go right through the origin, all that good stuff we're supposed to learn, and it would be a straight line like that. So in other words, as V increased, I would increase proportionally. And if you brought in something that was more resistant, then you might see it look like this, but it'd still be ohmic. And if it was another resistor, and it would, and if it was less resistant, so you should know the difference between these. So which one is the most resistant? You know, the one that has the highest the slope here, because the slope in all of these cases would be the resistance, because that would be V over I. Okay, so if we assume from conventional current that the positive side goes to the negative, so the electron flow would go this way. But, well, in actuality, it's not that way. It actually goes in the opposite direction, but it doesn't matter. But in conventional current, we would assume that the current is going in this direction, in this clockwise direction in this particular case. And we're just looking at how the voltage and current and resistance characteristics of a basic circuit. So, what offers resistance? So resistance from George Ohm was basically just a simple concept that in Ohm's law, V equals IR, and I don't know if that made any sense. I was just thinking to myself there just a minute ago, but not everything follows this Ohm's law that you were given in your book. So there are some things like a diode, which we'll do a little lab on one of these later, that do not follow Ohm's law. In other words, if you plotted the IV characteristics in this case, I think your book uses it as IV, you would see it go along with 0, 0. You'd be increasing the voltage, but nothing would be happening. It just goes along. These diodes just sort of have a voltage threshold, and then all of a sudden it just spikes up. And so that's not an ohmic material. And the same is true for sort of light bulbs. Light bulbs sort of give you the same thing, because light bulbs heat quite a lot as you use them. Your incandescent light bulbs, which, by the way, on January 1st of 2014 are not supposed to be made anymore. I think there's some people trying to fight that, but basically incandescent light bulbs are being phased out in the United States. So that's pretty interesting. The good old light bulb, but that light bulb, as you heat the filament heated up, the tungsten filament, chemical symbol for tungsten is W, and as it heated up, it sort of followed Ohm's law for a little while, and then it just started sloping off, and it did not follow Ohm's law, so it was not a proportional relationship. So these things are non-ohmic. Ohm, my goodness, they're non-ohmic, and but you know, this was a diode, and this was a light bulb. And an incandescent one at that, you could even talk about. It'd be interesting to see what fluorescent little bulbs would look like. But you know, oh well, we'll let you think about that. What else causes resistance? The conductors. So here's a piece of wire, and in that you have in resistance of the property of the conductor. And so a wire. So we're going to call this section of wire L. And in this section of wire L. So if we just looked at the resistance of section L, then we could say that this has resistance according to the resistance R in ohms is equal to rho L over A. So this rho is a property of the wire, and so that's not going to change. As long as you're using copper wire, you got the same rho. Aluminum wire, you got the same rho. Whatever, you know, if you use a semiconductor, same rho. RHO. You've seen me use that before. I could have made it better. Could have made it look like that. I probably should have. But but what are the two big thingies here? L. So how could I double R? Well, what if I double L? So 2. If I use this L and this L, so now I have 2L. there, L. And so now I've doubled the resistance. But what if I make the wire larger? So what if I have a diameter wire of, let's give it easy math, a radius of one unit, and I compare that to a wire that has a radius of 2 units. What's the difference in that area? So 1 unit and 2 units. Well, this would be pi r squared and pi r squared. So if I plug in r, so r is 2, so that's 4. So this is 4 pi, and this is pi. So that's 4 times greater. So the area is 4 times greater when you double the radius. So that means that A, the bottom part, the cross-sectional area, this is the area, and this is the length, and this is rho, again. And remember, your book doesn't really bring in the idea of rho, mostly because length and area are the most important aspects. So anyway, the area is quite a large player in this, and if you double the radius, you reduce the resistance by 4 times. Think about that. So if you get thicker wire, you get less resistant wire, and it would not play out. So let's talk a little bit more about this tomorrow, and let's stop this today, and we'll talk just briefly. Again, I'll bring in the concept of potential drop and a very simple equation on electric power, and we'll stop there. But I've already got 12 minutes in. I'm going to stop there. All right. So this is most of 5.4.